Hello everyone, this is Moushumi Akhtar from Bangladesh University of Engineering and Technology. Our work is on computing aggregates over numeric data with personalized local differential privacy. Co-author is Tanzima Hashem from same university. In this era of flourishing internet and smartphones, data collection from users has become easier and cost-effective. It has also opened the door for mobile applications and analysis. Data collection has a huge impact on research too. Collection of data and its analysis help researchers to perceive answers of their research questions. On the other hand, to grasp the behavior of a community, there is no substitute for the data collection. So we can say enormous amount of real-time data from users allows the government, business, and researchers to contribute in different domains for the improvement of the quality of human lives. Along with the benefits, the shared data can bring serious privacy concerns as they reveal sensitive information about the user. It may reveal private information about the user's health, habit, and preference. So it may bring serious privacy concerns. So what should we do? Should we share data with a trusted party? Considering the privacy issues, traditionally data is shared with trusted parties. They are responsible for ensuring the privacy of user data before sharing the data with others. But unexpected leakage of personal data from the trusted party may also cause a massive devastation, which happened to Netflix and AOL. In our research problem, we compute statistical aggregates such as finding the summation or the minimum values over numeric data. The identities of users are revealed for the authorization purpose, but the privacy of the data shared by the user is protected. The accumulator knows who are taking part in the system but does not know what is the actual data of a user. So obscuring user data from the central authority and from other users while facilitating the computation of aggregate functions is our main challenge. Data privacy has been addressed in the literature using different techniques. In the k-anonymity technique, a user's data is indistinguishable from the data of at least k-1 other users. A major limitation of the k-anonymity technique is that at least k users need to have the same data. In the perturbation technique, noise is added to the data without any theoretical guarantee of privacy. Sampling-based technique to ensure privacy only works well if the dataset is large and similarity exists in the data. Though cryptographic techniques ensure strong privacy, they are not feasible for real-world application because of their extremely high processing overhead. Secure multi-party protocols involve a group of users to compute aggregates where a user's data privacy is violated if all group members collude. In recent years, differential privacy has become an effective model to protect data privacy of users because of its theoretical privacy guarantee and less processing overhead. Main idea of DP is users provide data to a central trusted authority and the trusted authority protects user data from others by applying the concept of differential privacy. differential privacy adds noise to the data to provide rigorous privacy guarantee with an accuracy bound, so that no one can identify a user's data with a certain confidence level in the computed aggregate statistics. The major limitation of DP is that users need to trust the data accumulator. So a new term LDP has been introduced in research. In the local setting, users do not even trust the central authority. They want their data to be protected before leaving their devices without knowing the data of other users. For LDP, a user shares a randomized value instead of the actual one for a numeric attribute with an accumulator, such that no one can reverse engineer the actual value from the shared data with a certain confidence level. A number of approaches to ensure LDP for computing histograms and ordinal queries. In these approaches, authors developed a solution for protect LDP of numeric data for computing aggregates, example summation or minimum. So is our problem solved with LDP? A major limitation of LDP is that LDP assumes all users have same privacy level. Chance of privacy leakage exists if privacy level of one user releases. If the possible range of the values of a numeric attribute is large, the accuracy of the computed aggregates decays significantly. However, in reality, people may have background knowledge about the range of possible values for an attribute. For an example, though a salary attribute can have any possible numeric value, but in reality, people may know the range of salaries depending on the workplace. To overcome the above limitations of LDP, recently personalized local differential privacy has been introduced that gives users the flexibility to control their privacy levels. However, their work is limited to the counting query and cannot be extended for an aggregate function, as 1-bit protocol has been used. In 1-bit protocol, a random bit is sent using Bernoulli probability distribution from the user, and by tracing this bit, answers of different histogram queries are estimated. Now we are going to give a brief overview on PLDP. A randomized function f provides tau epsilon PLDP if and only if for any two values of an attribute t prime which belongs to say range tau, and for any possible output t star of f, the ratio of probability of generating t star when the input of function is t and the input of function is t prime is less or equal e to the power epsilon. Here tau defines a safe range for a user. For example, if the numeric data of any user is 700, the user may feel safe to share the data in the range 0 to 10,000. Privacy parameter. Each user can have her own privacy level. It means that the ratio of the probabilities of generating a random response is less than or equal to e to the power f. We consider the accumulator, other users, and eavesdroppers as adversaries. Users do not want their numeric data to be identified in a safe range with more than the required confidence level. The target of adversaries is to identify the actual numeric data of users, refine the safe range, and increase the confidence level of identifying the numeric data. We assume that users and the accumulator follow the protocol of the system while sharing their numeric data and computing aggregate. This gives an overview of our system architecture. We present our approach private as estimation of numeric aggregates to compute aggregates over numeric data while preserving PLDP. Pena uses a local random responser and exploits Bernoulli probability distribution to achieve PLDP. The general idea of our Pena framework is to collect random responses from users over a specified safe range. From these random responses, different aggregate is computed. Then Pena publishes the result. Here we can assume LRR as heart of Pena. LRR is run for every user separately. We use Bernoulli probability distribution to develop an LRR, which has been already shown in the literature as an effective way to ensure LGP of numeric data. A user first scales data using safe range tau. LRR generates two types of random responses. The probability of generating a random response among two options is calculated using the Bernoulli random variable. The calculation of the probability depends on the user's scaled value and depends on confidence level. It can be compared with a coin flip. The probability of generating head is calculated by Bernoulli random variable. Then the coin is flipped with the computed probability. If head is found, then the user responds with one type of random response. Otherwise, the user responds with another type of random response. We illustrate our proposed approach Pena with an example. Suppose the accumulator sets the safe range as 0 to 10,000. Let the actual numeric data of a user is 800 and confidence level is 0.2. Users scale their data to -1 to 1 using the safe range and generate random responses using local random responser. Without loss of generality, we show how a user computes her random response. The scaled numeric data of the user is -0.84. Probability of head tossed is computed as 0.46. The user either sends 10.03 with probability 0.46 or sends -10.03 with probability 0.5. Similarly, other users send their random responses to the accumulator. The accumulator estimates the aggregate over the received values from users and their safe range. For any user UI with privacy specification and any TI star, LRR guarantees PLDP. We have to show it. By definition of PLDP, we have to show that the ratio of probability when input is TI of LRR and when input is TI prime of LRR is less or equal e to the power epsilon I. The probability to compute TI star for TI and TI prime are shown respectively. This has been computed using Bernoulli probability distribution. Now this value will be less or equal the ratio of max value and mean value. The max value of TI is 1 and the mean value of TI prime is -1. We have put this value to the equation and we have found the value is e to the power epsilon I. So we can say LRR guarantees tau epsilon I PLDP for UI. We evaluate and compare the performance of our proposed approach Pena through extensive experiments. Since there is no existing work for PLDP over numeric data in the literature, we modify our work that is proposed for ensuring LDP of numeric data while computing aggregates and compare it with Pena. For LDP, the safe range tau does not exist and tau is assumed to be the set of all possible values for numeric data, and thus the achieved privacy level of the accuracy for the computed aggregate is not satisfactory to apply in real scenarios. For our experiments, we incorporate tau. We show our experiments for aggregate function average and minimum. Our approach is also applicable for other types of aggregates. We validate our proposed solution using the dataset IPAMS that contains 3.15 million total family income records of United States. We performed several sets of experiments by varying the following parameters: privacy level, the percentage of user participation, safe range. Table 1 shows range and default values used for each parameter. To observe the effect of one parameter in an experiment, others are kept in default values. Effect of privacy level. Privacy level controls the privacy of a particular user. Figure A and B shows that the relative error decreases with the relaxation of privacy level for both LTP and Pena. This is because with the increase of epsilon, more accurate user data are used in the application. For epsilon equal to 0.5 in Pena, values of privacy level for users are varied from 0 to 0.5. Whereas in the LTP-based approach, all users have same privacy level point. Both Pena and the LTP-based approach show similar levels of accuracy. This has been shown in figure. Effect of safe range. A higher value of the safe range ensures a higher level of privacy. We scale the maximum numeric value of the dataset to 1. Figure A and B show that relative error increases slowly for every 10% increase of the safe range for average application. For privacy level 0.3, Pena outperforms the LTP-based approach for aggregate functions average, and for epsilon equals to 0.8, Pena outperforms the LTP-based approach for aggregate function minimum. Of percentage of user participation, figure A shows that the relative error increases slightly with the increase of the percentage of user participation for aggregate function average. For 40% or less user participation, Pena generates error less than 20%. Figure B shows that the relative error remains almost constant over large dataset to evaluate minimum aggregate function. This result shows the effectiveness of Pena to handle large dataset to compute both aggregate functions, average and minimum. We have developed the first approach, private estimation of numeric aggregates, to compute aggregates over numeric data while guaranteeing personalized local differential privacy. Pena does not involve a central trusted authority and provides users the flexibility to control their privacy levels. Experiments using real dataset show that Pena outperforms modified LTP-based approach in terms of accuracy while ensuring higher privacy levels for users for both aggregates average and minimum.